Thanks everybody for coming. Thanks for inviting me to Bangkok. I will be talking about build systems, specifically about scheduling in build systems and very large-scale build systems. You'll notice a rabbit theme throughout this, and hopefully that will make sense as it goes along. The title of the talk is To Catch a Rabbit, Scheduling in Build Systems. When I think of rabbits, I think of things that move quickly, things that multiply rapidly, and also once they're gone, they're very hard to catch once they're gone. Just try to work with me on the metaphor part of things. We'll see how it turns out. So I want to start with a little description of works on ARM. I'm doing a talk about this afternoon, a Birds of a Feather session. The carrot in this rabbit metaphor is resources that we bring to people doing development on open source projects so that they have the resources that they need to do hardware testing, to do CI, hosted CI, their own CI, support for various things. So if you're trying to catch an open source project, one thing that you can do is provide some resources for it. Draw people in that way. And we also provide experience and assistance, expertise, sharing information between projects, try to bring people up to speed. It's funded by ARM, it's run at Packet, hosted at Packet with a variety of gear from a variety of our ARM server systems. So how do you measure success in this world? You're trying to build a bunch of software. Maybe you're just looking just at quantity, right? You say how many different systems, how many different builds did you do, how efficient are your systems. But maybe you're looking a little bit more towards measures of success towards a goal. The goal might just be sheer efficiency, like are our build systems working really well? Can we make them work better? But it also might be, are we building the right thing? Do we have the right priorities? Are we catching those brand new projects as they're starting and getting them ARM support right out of the box? Or are we more in the slow lane where we have very old projects that are no longer rabbits, they move slowly. So build systems in particular really have two jobs, right? You have a whole bunch of software you're trying to turn into code. The thing that you do first in almost every system, either explicitly or implicitly, is compute dependencies, identify what depends on what. And then once you have some understanding of what all there is to do, then in parallel, and especially in parallel on multi-core systems, on many core systems, your build system can execute tasks at the same time. You have to do the dependency analysis first so that you don't find yourself doing the last thing that's important, the first thing that's important last. Different parts of the build process depend on each other, so you have to have your compiler running before you can build your libraries, and you have to have your libraries before you can build certain things. And one of the things about build systems that's particularly complex is that the dependencies are not always obvious. So if your task is, for instance, to build TensorFlow, right? That's what we're going to do. That's our narrow focus. We're going to do machine learning. You discover quickly that TensorFlow is built with Bazel, which is a big Java application. It's like, oh no, all of our machine learning people now have to learn Java, right? And not only is it a big system, but it doesn't compile out of the box on ARM. So all of a sudden we're doing a porting task. It's like, oh, we have to have our porting experts. So the what to do first in a complex environment is not always obvious. And there are interdependencies. One of the things that you notice in a lot of build narratives is a proof of concept, right? We're going to say, do we have this code working? Let's prove that we've done it. So the proof point is a long handwritten description of what to do with lots of instructions and maybe some patches and some things that maybe be complicated, maybe a fork of something so that you can deal with architectural probabilities. That's fine as a proof point, but if you're really trying to move an ecosystem so that things that depend on other things that depend on other things all work, you have to have a much more evolved approach. An approach that doesn't depend on proof of concept, but that looks for repeatable builds, that looks for patches that are upstreamed and taken on and maintained over a period of time by the dependency projects. Sometimes this takes you down a path, even if your goal is to produce something for a particular system, you identify a common set of dependencies and you have to work on something else that's not on your first A list of things to do. And then once you have things built and your build system works, if you want things to continue to work, then you enter into a world of CI/CD where not only does that project that you depend on have to work now in your proof of concept, but that project has to continue to work for your architecture over time, over a long period of time. It has to be tested, and you have to make sure that it continues to do its stuff. So, you know, the rabbit hole that you sometimes go down is you're trying to build one thing, especially with brand new open source projects. You try to build one thing, oops, this almost works, but there's one little bit that doesn't quite work. You explore that one little bit. That thing depends on something else. That other thing depends on something else, and you find yourself working on something that you didn't intend to, but that's necessary. So if someone asks me where the state of ARM development is, almost always the answer is the code works on 64-bit ARM systems. There's a very small and shrinking set of common failure problems. But if you ask yourself the opposite question is, well, can I get that code, right? Does it get spat out on a regular time? That all depends on the build system. It's not enough that the software works. You have to be able to build and repeatedly build that software over and over. And more to the point, your build process has to be fast enough so that the software maintainer, the software developer, isn't waiting for your build to be spat out, right? If it takes them 3 minutes to do a cycle on their main platform and yours takes 20, then they're going to say, huh, we could speed up our build process 6x just by dropping support for your system. If you have hardware that's too slow to be self-hosted or too rare to be self-hosted, and I'll take the example of MIPS right now, the Go compiler team is considering dropping MIPS support, not because the code doesn't work, but because they can't find any hardware to do tests on. So you have to have a robust test environment for all that to work. And as the projects get bigger, the velocity of the test environment and the velocity of the build environment has to keep up. The biggest projects, the sort of hyperscale software development efforts, have lots of contributors, take lots of patches, have a demanding build environment, and you can't imagine to jump to hyperscale usage, even if the code works, right? It's not enough that the code does what it needs to do. You have to have all that build infrastructure to keep up. So I want to talk about some specific build environments. This is going to range from things that everyone knows about and everyone knows about better than me to research environments and strange things. Go briefly through this. So starting with Make, like everyone knows about Make, good old Make. Variants of that, things like CMake, which sort of splits apart the one part from another and does things. A build system called Ninja, which was described as like assembly language as opposed to like code that you can read. And then various things that generate Ninja files. Bazel, which I mentioned earlier, which has its own Makefile-like language called Skylark that's used in Kubernetes and TensorFlow. A research system called GG, which makes incredibly interesting use of AWS Lambda as a backend for doing infinite levels of things. There are many others. There are about a third as many build systems as there are projects. And that may be extending that thing to them. But there's lots of ways that people build software. And if your favorite isn't here, that's not because I know about it, but there's a standard font size for the slides, so I can't fit it on. So Make a Makefile is a Turing complete language. You can do anything in Make, any possible thing. Make, if you have a big project, Make takes a long time to start up because it's busy reasoning about everything it possibly can do. And if you have a very big project and you're not doing anything, right, the sort of null case of you do a make and then again you do a make right afterwards and there's nothing to do, it can take a very long time for that second make command to do nothing. And in a big project that's trying to have a high velocity of builds because you're trying to keep up with the large number of developers doing patches, it's very slow. It's slower than it needs to be, and also because Make sort of computes a set of things to do at the same time that it's doing it, you can't really reason about what your dependencies are, right? There's no easy way to spit out a big diagram of what are we up to. So beyond Make dividing up the problem, the LLVM compiler is a good example of this. It has Makefile rules written in CMake, which is another descriptive language about dependencies. But CMake, instead of directly scheduling the build jobs, it creates output files with Make or this Ninja project. And so CMake becomes sort of a meta build system. It doesn't actually do the work. It simply describes what needs to be done, and then some other system does the work. So that's sort of dividing the how do we build our software into two parts, reasoning about what we're going to do, and then executing that graph, or computing something off that graph. So the meta build systems, a meta build system sounds really fancy. It's really a system for computing dependencies and generating a Makefile or generating a build file for something. It effectively bifurcates the problem. It splits it. It splits it from build the system to reason about what to do and then do that thing. And in a good meta build system, you leave behind some artifacts that you can make some sense about. So if you're building something very large and has a lot of dependencies, you may want to audit that. You may want to say, you know, how many of these dependencies do we have use a license that we don't like? How many of these dependencies that we have have security issues? How many ones are written by a competitor that we don't want to engage with? How many of them don't have maintainers? So breaking up that problem of what do we depend on versus what are we going to do is important. And it's especially important as the project size gets bigger. So if the project is very large, it can be, and your Makefile is very large, and Makefile is very complicated, it can be hard to sort of manage reasons for why you're doing stuff. And generally, as the system gets bigger and the Makefiles get more complicated, or the CMake files get more complicated, that big system is a sign that you've achieved a level of success, a level of project maturity. So again, in the sort of build the thing that builds the build the thing that builds the thing that builds the thing, right? We're getting meta about stuff. Two examples of these. One is used to build Chromium. It's called GN. It generates build files that Ninja uses. GN replaces an earlier thing from Google called JIP. It's not yet ported to 64-bit ARM. So if you want to build Chromium absolutely from scratch on ARM64, your first task is not to build Chromium. Your first task is to port GN. Similarly, Bazel is a build system from Google. It's a port of their Blaze internal system. It assumes an environment where compute resources are effectively infinite. which is very different from a lot of people doing ARM development on small desktop sort of repurposed mobile cores or whatnot. Bazel is traditionally built with itself, so you have a bootstrapping problem of how do you get up to speed. It's written in Java. I try to build Bazel every time it comes out, a new version comes out, and inevitably I find myself discovering bits of the Java environment that I don't know. So, it's probably solvable with enough people and enough sort of elevation of the fact that it's interesting. Bazel is used to build TensorFlow. So if you want to do machine learning and that's your library environment, you're implicitly dependent. You thought you were studying machine learning and actually you're studying Java build systems. So that's one of the challenges of software at scale is that software that's developed at scale is often developed with build systems that are built at scale. And I also have a couple of, next, examples. I thought I had some examples. Yeah, here we go. So I want to think about build systems as an artifact, as a thing. If you're a machine learning expert, the last thing that you want to do in the world is reason about build systems, right? You're an expert in machine learning, you want to work on your codes, whatever, and the build system is like not the level of expertise. If you're building a big system for one platform and someone wanders along into your project and says, hey, can you give me a binary for my platform? If you hadn't thought about portability from the start, that's going to be a challenge because you may have baked in a bunch of assumptions, accidentally, incidentally into your code. You're pulling down a binary to do some task and you didn't realize that you had to think about binary compatibility. So often the build systems are the primary source of compatibility issues, not the code itself. And I have to say, the more I learned about these various build systems, which are complex in their own right, the less confident I was that I could actually say something about them that was reasonable. So here's an example. There's not a lot of information about GG. It's a research build system, originated at Stanford, very much a research project, right? A lab doing things. It very much like the CMake and Ninja breakdown. It has a two-part build process. It takes a big project and divides it into things that are called thunks, which are combinations of code and instructions and dependencies that this big system can build on. And then part two of the project dispatches as many jobs as it can to AWS Lambda all at once. So imagine you have a project that has a build process that has 6,000 steps. With GG, the model is we're going to do all 6,000 steps at once, right? We're not going to schedule, we're not going to wait, we're just going to do them all. And if something has a dependency on something else, it'll just block until that dependency is resolved. It's parallelism at the largest scale that I've seen, that if you're not living inside a hyperscaler that you can imagine. I hope everyone in this room knows what Amdahl's law is. If you've ever dealt with high core count machines, Amdahl's law, which dates from the 1960s, basically says you can parallelize all you want, but at some point you're going to run into a serial processing step, and that's going to be the slowest thing in your world. And the results from GG on building a non-trivial software platform bear this out. So about the build had about 6,000 steps, something like that. The first 5,900 of those steps take about a third of the time. The next 70 steps take another third of the time. And then at the very end, this is a great graph. It goes sideways, almost like, it looks like you're going to be done, and then it goes straight up for a while. Because a couple parts of the build process are serial. The thing that does strip on a binary, the thing that the archiver I think they were using a linker that was serial. So even though you had you were doing 6,000, make minus j 6,000, it still took less, it took more time than it might have. But remember, this comes from a world where you're going to, instead of trying to optimize for a 1-core machine or a 4-core machine or a 16-core machine, you're saying, we've got all the cores in the world. How are we going to do that? And I think that mind shift from scarcity of resources, where I've heard people say to me, well, we'd love to do this, but we just don't have enough kit. We don't have enough cores. Understanding that some of the world that's doing open source development is living in a world where there's infinite resources, and time is the scarce resource. So, another really interesting build system is from the NixOS platform. NixOS is a purely functional operating system. The idea behind NixOS is that if you have a dependency on another component, you can rely on a operating system-wide build cache, so that you can pick, if someone else has ever done that particular combination of things before, you can rely on those components. So very high level, very aggressive caching of builds, reproducible results, the ability to pin your dependency on a particular version of something and have multiple versions installed at the same time, so you don't have conflicts of that sort. We've been working with the NixOS team to provide them with some resources to exercise basically all of the hardware at packet. Just like make sure that every system that we have, whether it be ARM or x86, can run all this stuff and build itself, right? And keep up with the incredible pace of change of open source software. And that's been very enlightening in terms of understanding how to help manage and help provide resources to a big build system. There's a couple examples where the build systems get very aggressive about building things. So you have a big project you're doing, it has a lot of change, there might be multiple changes happening at the same time, and you're trying to accelerate the speed of everything. So rather than testing changes sequentially one at a time, two systems, Uber's SubmitQueue and OpenStack Zool, do what I would consider speculative execution on builds. They're going to say, great, we have 10 patches in the queue. Let's apply them all, try them all, right? Simultaneously, we're going to try them one at a time. If they all at the same time work, that's great. We'll take the whole thing. If something breaks, we'll backtrack and we'll do a bunch of builds in parallel and figure out where to bisect the things that are good and the things that are not good. Similarly, for speculative builds, and I guess in a world where you have infinite amounts of hardware, I was reading about one of the Google build systems that could execute builds locally and also in the cloud, and take advantage of caching and queues to make sure that if you wanted things to go faster, you didn't decide whether to build in the cloud or to build locally. You simply always built things in both places. And if your job completed on one, then you just kill it on the other and start with the next thing. Again, this world of infinite resources where time is really the critical thing. So why do we have these CI/CD systems? Why does it matter? When projects have a lot of contributors, when they have a lot of dependencies, when a lot of things depend on them, it's crucially important to get rapid feedback on the results of change. If you're trying to keep up in a world where people are constantly doing development, then the inability to get feedback on changes you can lose a lot of ground. And you can lose ground very quickly. Someone introduces an incompatible change for your architecture, but not for their architecture. If you're building once a day, it'll take you 24 to 48 hours to discover that something has gone wrong. In the intervening time, 3, 6, 8, 12, 15 things have happened. So you have to go back and do the expense of bisect effort to try to figure out where things have gone on. So the faster you can get feedback on evaluating changes, the better. You really want builds to be reproducible so that every time you build something, you get the same thing. So it's not difficult. You want the test to work out as well as you can. You want to understand your dependency chain so you can be mindful about risks and make some library decisions that work. You want incredibly complex systems to build in a very short amount of time, which is a big challenge. And then you want this build infrastructure to be inexpensive because you don't want to spend more than you have to on the things that build stuff because you want to use that machine pool to actually do things. In general, no CI/CD system does that, right? There's always trade-offs, cost versus speed versus complexity. So it's a challenge. One of the things that's a particular challenge in the world of setting priorities, right? You want to make sure that you're doing the right thing, you're working on the right projects, that you have high-level goals that you're trying to exercise. If your customers are asking for specific things that are the most important things on their agenda and the most important things in their roadmap or their blueprint, and they're not asking for something else, then that's a reasonable thing to reflect upon. But open source developers often depend on things that are not listed on the outside of the box, right? The fact that you're doing development in one language, but the build system is actually written in another language means that implicitly, in order to support that whole system, you have to have support and expertise across a much broader set of things, not just all the runtime dependencies, but all the build time dependencies. And if your tooling is marginal and your process works, but it's super slow, an example of that is a lot of Python development work right now on ARM64, where on x86, a lot of the what are called wheels are precompiled, and you can just grab a binary from somewhere else and install it, whereas on ARM, the wheels are not precompiled, and so if you do pip install SciPy and you want to do some scientific computing, it'll work, but it'll take half an hour to build all the parts from scratch. Whereas on the other system, it might work, but it'll take 30 seconds to download a binary. And so understanding how complex the dependency chain is can really affect your priorities about what you need to work on, because often the narrow things that you think you need to work on have dependencies over into other ecosystems that you also have to take account for. So what are the challenges specific to ARM for CI/CD? What are the things that I've run into in the course of helping 100+ projects and actively looking on GitHub? I have a search that I run that says, looks for ARM64 and for issues that people open up and what they've run into. There's a couple things that are really ARM on ARM challenges. There are hosted build systems, hosted CI systems like Travis, which is the one that people usually come to mind first, that don't have native ARM support. Some of the CI/CD systems do, Drone and Shippable and CodeFresh, but some other ones don't. And in a world where people don't always try them all, they try the first one that comes to mind, the lack of native support doesn't help the process. So to get around that, people use emulation. They use QEMU. QEMU is a great system, but it has its limitations. The most general way of describing it is that emulation is imperfect. It will always be imperfect. And in particular, things that do just-in-time compiles that are rewriting the instruction set or rewriting the instruction stream as things go on are a real challenge for those emulators. People have to work in sort of a cut-down set of things. There's generally in the ARM ecosystem a shortage of high-powered cores in high-memory machines. right? The total number of cores of machines that have 100 gigabytes of memory or more in the ARM world is orders of magnitude less than there are for some other architectures. So the projects that need lots of resources systematically have a hard time getting them. I think people tend to underestimate the depths of the dependencies that people have to reason about, both because systems get more complex all the time and you don't realize it, but also because people doing development in other ecosystems just pick seemingly at random from things that they need. It's like, oh, we need a queue system. Well, let's bring in RabbitMQ. Well, that brings in all of Erlang. You didn't realize that you depended on Erlang, but suddenly, welcome, suddenly you do. Or we're going to use the latest version of this, and so you have to be at the tip of things. Or on some projects, they say, well, we're going to use an old version of that because we know that it works, but that old version hadn't been ported to other architectures yet. The dependency solving, trying to understand which versions of which things are all compatible, is a very hard problem. And it's hard to reason about, and it's hard to execute on. So that's a challenge. And then, one of the real challenges is that some very large design and development systems really are x86 first, and often x86 only. So if you have a big company producing a big system and they decide to open source it and they sort of eject it from their world, there can be a lot of things that they weren't ever thinking about in terms of portability. And that can be really difficult to remedy. Those are the hardest sort of systems to rescue because they've got dependencies baked in up and down the food chain, the build dependencies, the runtime dependencies. No one has ever thought about portability, and that's a challenge. So again, goals, right? What are we trying to do? We're trying to catch rabbits. We're going to try to catch these really fast-growing, active projects. A lot of it is going to have to be somewhat selective, right? There's no way that with a finite amount of resources, you can solve all the world's build and portability problems. But what we are trying to do is catch developers, try to find people who have talent, trying to find people who have awareness of build systems, and enable those organizations that do get it, that do understand that portability is important, that are working on things where it's not an afterthought, but it's really a primary goal, and help them grow. So this is Bugs Bunny. It's not quite riding a unicorn, but this is the closest I could get to a unicorn in this world. If everything goes right, we're not just enabling infrastructure that we're never going to hear about, but we're really enabling fast path growth in a world where there's resources to grow, right? There's ways to grow things. So with that, I guess this is the generic thank you slide. With that, that's an overview of things. I realize that build systems are incredibly complex in their own right, and that the examples that I gave do not cover the entire world of how software is built, but I'd be very willing to take questions. Okay, thanks very much.